Our second speaker of the day is Salvador Grimozzi. Salvador has a degree in physics from the University of Buenos Aires. He is PhD Fellow of the CONICET and a member of the Galaxies Models Group. Salvador's talk is about chemical enrichment and assembly history of the Milky Way-like halos in the ARTEMIS simulations. The participants may ask questions at the end of the talk and can send them also using the chat. Salvador, you have 30 minutes for your talk, and I will let you know 5 minutes before. Thank you. All yours, Salvador. We are listening to you.
Thank you, Cecilia. Hello, everyone. I'm Salvador Grimozzi. I'm a PhD student at the University of Buenos Aires, and my supervisor is Maria Emilia De Rossi, and my co-supervisor is Andrea Font. The title of my presentation is, as Cecilia said, Chemical Enrichment and Assembly Histories of Milky Way-like Halos in the ARTEMIS Simulations. The structure of the presentation: an introduction with the motivations. I'm going to present you the ARTEMIS simulations. I'm going to talk to you about how we identified disrupted and surviving dwarfs in Milky Way-like halos, which is basically these dwarfs are our object of study, our main object of study. I'm going to present you the results we obtained, and finally, it's some conclusions of our work. So first of all, as you may know, in the lambda CDM cosmological model, galaxies grow hierarchically, where smaller structures merge to form bigger ones. Basically, we have this is the case, for example, of the Milky Way, and Milky Way-like galaxies increase their stellar mass by accreting smaller structures, which are known as disrupted dwarfs, and surviving dwarfs are those galaxy dwarfs that were not accreted but by Milky Way-like galaxies, but they are gravitationally bound to them. For example, in the case of the Milky Way, the most known surviving dwarfs are the Magellanic Clouds, which were not completely accreted and disrupted by it, but are gravitationally bound to the Milky Way. As you can see in this picture is from a work from Naidu et al. From 2022. They studied observational data from the disrupted and surviving dwarf populations of the Milky Way, and they discover these trends in the mass metallicity relation in the left panel and the alpha enhancement versus mass relation in the right panel, where they found that for the Milky Way, disrupted dwarfs present lower metallicities and are more alpha enhanced at fixed mass than surviving dwarfs. So we tried to carry out a similar analysis in the ARTEMIS simulations. Now, the ARTEMIS simulations is a suite of 45 zoomed-in, high-resolution hydrodynamical simulations of galaxies in Milky Way mass-like halos. So we have 45 different halos. I'm going to I call them main halos or main hosts. So every time I use any of those terms, I'm referring to these 45 Milky Way mass-like galaxies. It uses a flat lambda CDM WMAP9 model. These are the cosmological parameters, and it is run with the same code as the Eagle simulations, which is a modified version of the Gadget 3 code. Anything related to to the Eagle simulation. You can find it in Shea et al. From 2015. The difference in Artemis is that they adopt a recalibrated stellar feedback. The parameters that define the stellar feedback are changed with respect with what there is in Eagle, and well, so we have 45 Milky Way mass like halos in periodic cubic volumes of with a side length of 25 megaparsec, and these are they need the dark matter particle mass and the initial gas particle mass. And unlike in Eagle, it has very numerous physical processes are modeled using a subgrid model, which basically includes star formation and chemical evolution, metal-dependent radiative cooling. It also tracks and simulates the formation and the evolution of supermassive black holes and therefore the AGN feedback from them. It also takes into account the stellar feedback from supernova, from type 1a supernova and type 2 supernova, and stellar winds and AGB stars. And it's also worth mentioning that 11 different element species are tracked individually. So we have among them is, well, of course, hydrogen and iron and magnesium, which will be two elements that which are two elements that we studied in our work. This is an example of the mass metallicity relation and of the ARTEMIS simulations compared with some observations at high and low mass. Okay, so having introduced the simulations, I'm going to share how we uh, started our work. I mean, the first step is obviously to identify the disrupted and surviving dwarfs to create our original pool of data, our original sample that we're going to study. So what we did basically was that we consider a surviving dwarf any galaxy dwarf that is located within the R200 of their main host at redshift 0. So basically at redshift 0, any galaxy that it is closer, which has a distance to the main halo that is smaller than the R200 is a surviving dwarf. For those who doesn't know, the R200 is basically the radius measured from the center of the main host within the density is 200 times the critical density of the universe. So that's how we identified surviving dwarfs, which was the simpler of the two populations. The other is disrupted dwarfs. Now, in order to identify disrupted dwarfs, which were galaxies that were completely disrupted and accreted by the main host, we constructed the merger trees of both of every single Milky Way mass-like halo. So the first step is to construct a merger tree. As you can see here, this is the merger tree. And then what we do is we identify the main branch of the merger tree, which is this is the main host, the main halo at redshift 0, and this is its main branch, which is composed of its main progenitors. And as you can see, at every snapshot, each of these dots represents a different snapshot, which is a different time in the simulation. We identify which is the main progenitor of the main halo. In this case, for example, for snapshot 20 is the green one. And we have the descendant ID, which is basically the ID of the following of its of its main of its descendant, and with that descendant ID, we're able to track which other galaxies in that snapshot are going to merge with the main branch in the following snapshot. In this case, the blue ones. So these three galaxies in blue and the galaxy in green have the same descendant ID. And knowing that this green galaxy is part of the main branch, we can assure that these three dwarfs are disrupted dwarfs of the main halo. And also we have, as you can see here, these secondary branches, we have the evolution of these dwarfs in time. So basically, we have all the data that we can take from the simulation for each disrupted dwarf. This is just an example of how of the tracking of a main host, which is in blue, that appears in the simulation at redshift 10, and we track its movement until redshift 0. And these are disrupted dwarfs that, as you can see, we have several examples. For example, this one was originated far away from the main halo, but at some point in time, it was captured by its gravitational potential. It was bound to the main halo and follow it until it was completely accreted, and the same happens for the red and orange one. Okay, so another important thing that I would like to discuss is that in the case of disrupted dwarfs, we had to define the time of accretion, specifically the ratio of accretion, which basically means at which redshift we can consider the dwarf to be completely accreted or to be accreted by the main halo. What we found something very interesting, that at some moment in time, the disrupted dwarf is accreted, it crosses the R200 of the main halo, but interestingly, while the dwarf is inside the R200, it continues to increase its stellar mass. So these dwarfs continue to form stars even inside the R200 of their main host until at a certain point their stellar mass reaches a maximum, and then it starts to decrease, which is we attribute this to the fact that it's being completely disrupted. I mean, its particles are not are being now part of the main host. So basically, what we have for every disrupted dwarf is that its stellar mass increases, reaches a maximum, usually inside the R200 of the main halo, and then it starts to decrease until it disappears from the simulation. So basically, we decided that we will label this moment where the maximum mass is reached as the ratio of accretion, and the moment where the dwarf crosses the R200, which is usually not the same as the one before, is called this Z accretion R200. Mainly, when I talk about disrupted dwarf, we are going to use this ratio of accretion. Okay, so that's just a clarification, because sometimes the ratio of accretion is defined in another way. So here we use this definition for ratio of accretion. Okay, so having shown you how we identified these populations, these two populations, I'm going to talk about the results we found. So the first of all, we studied the idea behind this work is to establish a connection between the chemical enrichment and the merger history. So regarding the chemical enrichment, we studied the mass metallicity relation of the Milky Way the mass metallicity relation of ARTEMIS simulation, and we compare it with the Milky Way using the data from Naidu et al. These are what we found. In the left panel here, you have the scatter plot of the MCR. Each of the dots represent a different dwarf. disrupted dwarfs in purple, surviving dwarfs in green. The red line, the full line, is the fit for surviving dwarfs in ARTEMIS, and the purple one is for disrupted dwarfs. And in black and blue, you have the data from NIDU for both surviving and disrupted population. And as you can see, in the case, for example, of surviving dwarfs, we have a really good agreement. The slope is almost the same, comparing the red full line with the black dashed line. It's important to know that this black line shown in NIDU is from a previous work from Kirby in 2013, which was computed using observational data. But it's also interesting to note that in the case of disrupted dwarf, the mass metallicity relation in ARTEMIS is steeper. And it's also not only steeper than what's reported in IDO, but it's steeper for disrupted dwarfs than for surviving dwarf. So first we looked at this and we wanted to know why did the steep of the MCR change between two populations. So we studied the evolution in time of the mass metallicity relation, what you can see here in the bottom right. So just remember that surviving dwarfs, all the data from surviving dwarfs comes from redshift 0, okay? Whereas all the data from disrupted dwarfs shown here comes from the redshift of accretion, which is usually greater than 0. So basically, in the surviving population, we have data from a single redshift, whereas for the disrupted population, we have data from different redshifts. And as you can see here, the mass metallicity relation evolves with time. So as we go to higher redshift, the metallicity decreases, and also does the mass. As you can see here, the mass range covered by the simulation moves to the right as we go to redshift 0. So basically what we have is that the normalization of the MCR decreases with redshift. Then when we mix different disrupted dwarfs from different redshifts, and we compare it with surviving dwarfs from the same redshift, we find that the mass metallicity relation of disrupted dwarf is steeper than that of surviving dwarfs. And this is the explanation of it. We also studied the correlations between the mass metallicity relation of both populations with different properties. For example, with redshift of accretion and with star-forming gas fraction. And as you can see that for disrupted dwarf populations, which are the two top panels, the least metal enriched and the least massive dwarfs tend to show higher, sorry, there's a mistake here, higher ratio of accretions and higher star-forming gas fraction. And it's also interesting to note that these white dots represent disrupted dwarfs with 0 star-forming gas, and they do not follow the general trend because if they did, one would expect these galaxies to be located with the dwarfs in blue, right? But unlike those, they are located in the low mass range. So that would imply that there is a small population of dwarfs with very little mass, with very little star-forming gas and low mass that follow a different trend. In the case of surviving dwarfs, the correlations here are weaker, are not that notorious as in disrupted dwarf. In this case, in surviving dwarf, as we don't have a CF accretion, we define the C50, which is the redshift at which they reach the 50% of its maximum stellar mass. That's C50. And as we say, there is no much correlation. We can see that for the lower mass, we have a wide range of C50s. And in the case of the star-forming gas fraction, it's interesting to note that most low-mass dwarfs present practically no star-forming gas, and combining what we see here and what happened with the disrupted dwarfs with zero star-forming gas, we see environmental effects like could be like ram pressure stripping, uh, when these effects which are present, especially when they get closer to their host. So we also studied the alpha enhancement of the uh, of both populations. In order to study the alpha enhancement, we follow the magnesium abundances. We compare them with the iron abundances, since magnesium is an alpha element. We found that their abundance of alpha elements over other elements like iron is bigger. Another possible explanation is the effect of supernova. As you may know, type alpha elements are mainly synthesized in type 2 supernova, whereas iron is synthesized in both type 2 and type 1a. But type 2 supernova occurs a considerable amount of time before than type 1 supernova. So for galaxies that didn't have time to evolve and were accreted fast by their main halo, uh, we can find a greater abundance of alpha elements because their star in their stellar populations, there was a bigger number of type 2 supernova compared with type 1a. So then I'm going to talk about the merger history and trying to find a connection between merger history and the chemical composition. In order to do that, we decided to plot each of these dots here, unlike in the previous graphics. Each of these dots represent the data from all the dwarfs of an individual main host. What we have here is the weight mean alpha enhancement and the weight mean metallicity. And in this plane, we decided to select the 6 closest galaxies to the Milky Way in this plane, which are these 6 here. We call them the S6 subsample. And we found that this sample not only has similar uh, alpha enhancement and metallicity mean values, which to the Milky Way, which comes from their very own definition, but they also present the Milky Way mean C of accretion is within the range of this sample. So that's a very good idea. A very good new, because it means that at least uh, we can say that the merger history of the Milky Way can be similar to them. And what's more, in a work by Dillamore in 2022, they identified several main hosts in ARTEMIS that present a Gaia sausage Enceladus feature. Gaia sausage Enceladus was a major merger uh, uh, experienced by the Milky Way of a disrupted dwarf of 10, I think that it was 10 to the 8 stellar masses that occurs a few giga years ago. And the good thing is that 4 of our 6 halos of selected halos in this subsample also present a Gaia sausage Enceladus feature, like the Milky Way. Then we decided to study a few other properties and compare them between what we found in the Milky Way and what we found in the S6 subsample. In particular, we feed it a linear regression for both the MCR and the alpha enhancement versus mass relation, and we tried to see if there was a correlation between the slope of these two relations and the merger history. In this case, for we used the mean ratio of accretion, and we found like very weak correlations, as you can see in the two graphs, the one in the middle and the one in the bottom. So there is not that much connection between the fit, the steepness of these two relations and the merger history. Uh, Another important thing that we can take from here is that for example, G26 is one of the galaxies of our subsample that is closer to the Milky Way. Although it's also important to note that G26 is not part of those galaxies studied in Delamore, so it doesn't experience Gaia-Sausage and Enceladus merger. So this would tell us that, well, maybe these two values are not that important, are not that connected with the merger history as we could have supposed. But another thing that we decided to study that was also mentioned in NIDU was the role of the environment in what happens with disrupted and surviving dwarfs. In their work, they have this hypothesis that the difference observed in the chemical composition of both disrupted and surviving dwarfs could be explained by environmental processes, by the origin, but for the hypothesis is that most disrupted dwarfs were originated closer to the Milky Way and a denser environment than surviving dwarfs. We wanted to test this hypothesis in ARTEMIS and see what we can find. In order to do that, we defined we used the theta 5 parameter, which is basically takes this sum is with the 5 closest neighbors. We take the mass and the distance of the 5 closest neighbors to a certain galaxy to compute its theta 5. It's important to note that in this calculation we exclude the main host, of course, so it only takes into account galaxies that are not the main host, the 5 closest neighbors to a dwarf that are not the main host, and all the data that we have here. These are the median relation, and these are the 25th and 75th percentile. In order to compute all these relations, we only consider the theta 5 of disrupted and surviving dwarfs when they are located outside the R200 of their main host. This is important to note because when they are inside the R200 of their main host, now the environment, it's not the environment we consider of interest because they are already accreted. So here we found that for most redshift, disrupted dwarfs evolve in higher density environments. As you can see here, the median theta 5 is larger for disrupted dwarfs than for surviving dwarfs. We also studied this same relation for the S6 subsample, are these color lines here. And as you can see, they tend to follow the general trend. There are minor differences. For example, G1 tends to be in a higher environment for certain periods of time, but most of the time they follow the same trend. Of course, at late redshift, where their number of disrupted dwarfs is small, their values tend to differ, and the same for disrupted dwarf. We also studied the distance between each dwarf and their main host. These are the histograms at redshift 2 and redshift 1, where you can see that disrupted satellites are closer, in general, are closer to their main host than surviving dwarf at both redshifts. So basically taking what we have here and the information from the study of the theta 5 parameter, we can say that ARTEMIS predicts the trends predicted by ARTEMIS agree with the hypothesis of Naidu. Disrupted dwarfs were formed in denser environments and closer to their main host than surviving dwarfs. So now I'm going to name the conclusions of our work, which are they all come from what of the results we obtained. First of all, as you can see, the ARTEMIS simulations agree with the observations of the Milky Way regarding the slope of the stellar mass metallicity relation of both disrupted and surviving dwarfs. As I commented before, we saw that the slope of disrupted dwarfs, of the MCR of disrupted dwarfs, is steeper, and this is than in surviving dwarfs, and this is due to the increase in mass and metallicity towards lower redshift. Basically, the change in the normalization of the MCR with time. We also find, like in Naidu, like in the case of the Milky Way, that a fixed stellar mass, the disrupted population is more alpha enhanced, and we attribute this to a shorter and more bursty star formation, and it can also be related to time delay between different types of supernova. We were able to identify a small sample of main host, which are chemically closer to the Milky Way, and 4 of them present a Gaia sausage and Enceladus feature like the Milky Way, which is also a good result. And we also, and by studying the environment, we found that disrupted satellites originate in denser environments and closer to their main host than surviving ones, which supports the formation scenario that was proposed by Naidu. And that will be the conclusions of our work. And if you have any question, any comments, I'll be happy to answer them.